Hi, I'm Jason Loasching, and I'm going to be over advances in radar target classification. Now, radars are really good at determining the range of an object or its velocity, but it's not really good at determining what the object is, whether it's a plane, a car, or a chopper. So, this research I'm going to be presenting to you really aims at drowning out noise and creating unique graphs that identify specific objects like a car or a chopper, a specific car, a specific chopper, that we can then hopefully feed into AI to provide real-time identification of that object. Now, I personally like this because it's a blend of the radar aspects we talk about in class and AI. I also actually have a job lined up with Lockheed Martin when I graduate, and I could be very well working on radars. Now, the first thing we have to understand is the micro-Doppler signal model. Now, as an object moves, there's a Doppler shift created by the object. But say a chopper, for example, has those spinning fan blades. Well, those blades also create its own Doppler shift, but it's very small compared to the large Doppler shift created by the moving helicopter as a whole. And this is called the micro-Doppler. So this model takes the bulk Doppler and sums up all the tiny micro-Dopplers created by this helicopter and adds them together to create our signal. Now, we can take this and convert it into a spectrogram, and you can actually see the micro-Doppler, the little ripples created by the micro-Doppler within the large bulk Doppler. But in order to get the spectrogram, we actually use short-time Fourier transform, which is used by taking a sliding window of the Fourier transform across the whole input signal, the whole Doppler. As you can see here, you take the Fourier transform of the signal in a finite amount of time, and then move that time over a little bit, move that window over, and then take it again. This allows us to create a spectrogram. Now, the next graph we're looking at is a cyclostationary analysis of the micro-Doppler. What this does, it computes a autocorrelation by correlating the signal with its frequency shifted over. So it's the same signal, just shifted over a little bit in the frequency domain. And what this does is it allows us to detect hidden periodicities in the micro-Doppler that regular standard autocorrelations cannot provide. So now we can create a contour plot that incorporates these micro-Dopplers that other contour plots cannot provide. And now we have another unique identification device or graph that identifies a specific helicopter or car. Last thing I want to look at is the SAR ATR. Now, the SAR is a synthetic aperture radar, and what it does is you take a radar antenna and you put it on a moving object, and what this moving object, by having it move, creates a synthetic larger aperture of this radar so it can pick up more when it's not capable of doing that normally. Now, this SAR actually created all these images here, and these are real images of tanks. So the 2S1, the BRDM2, these are all real tanks. And you do is you put this into this ATR, a auto target recognition system, usually a neural network of some kind, and that will identify what the object is. Right now, the big thing is convolution neural networks, because convolutions is needed within radars already. So it allows you to kind of cut out some steps there. And the whole idea is to take the spectrogram, take the contour plots, and take these images and feed this all into an AI that it can automatically detect these things. So really, the future of radars is not only determining its velocity and its range, but determining what exactly the object is. That way, for maritime applications or wartime applications, we know exactly what the objects are as well. It's really good for that. So that's what this research is, and I hope you enjoyed. Thank you.